Since the last update, there are some people contact me about a intermediate level of the OpenFOAM operation. We might to introduce a bit more beyond the geometric or complex geometry construction. That's what we did in the last sessions, and that's why I introduced the part 3. So for the conjugate heat transfer in the real applications, we might consider the source items. What is source items? Which means there are some heating sources arising from other, like for example, heating conditions, right? Not only the fluid flow, but also extra heating source. And also because of such heating, there might be extra change of the phases. For example, the solidification. For example, ice formation is kind of solidification, or ice melting because of the increase of the temperature change, because the increase or decrease of the temperature. So this all can be done by using the FE options, which is a very powerful tool in the OpenFOAM. So that's what we are going to explain in the later stage. So because I have done the previous problems, it can be easily converted into application that will use the source items. So this is actually my first problem. So if you want, I will copy this here. So if you want to check what it looks like, you can check the previous video from conjugate heat transfer from scratch, section 1 to 8. There will be details of how to set up the operations or the meshes for this problem. I'll explain here now again. So we have the hot air inlet and hot air outlet, and also the cold water inlet and cold water outlet. So the two fluid domains are separated by aluminum block. So that is very typical for our heat transfer applications. Two medium separated by solid layer to transfer the heat. But now I have an extra addition of the heating sources, right? So we are not only heating or cooling. For example, we want to use water to cool the hot air, but now we have another source that brings heating in the aluminum block. For example, the heating sources, which means it keeps bringing some like heatings in kind of a domain which is 20 millimeter wide width in the center, and want to know what will be the final or the steady conditions looks like for this scenario. Again, check my previous videos if you want to set up previous all of the domains by using the block mesh and all the condition settings, because now for the conjugate heat transfer, I'll reuse all of them. Except before the running, right? So all the system constant, the mesh region definitions, the flow conditions, they all need to reused. Now I will just copy from of the previous one. This is my previous one to a new folder. Then I can reuse it. So I will go to my OpenFOAM terminal. So I will just copy R, which means all the sub files from CHT demo to the CHT demo. I will rename it as CHT demo source. So this will give me a folder that has been created now. So it is created now, and with all the previous conditions and even the calculations, right? Now I don't need calculations because I want to change the So I will delete all these results files. So these results files being deleted. There are some extra files not needed just for. So this is all this. If you check the system, there are some system folder. Again, I want to remind here, so the domain 0 is for air, domain 2 is for water, and the aluminum block is defined as solid, right? So these are the files that is because of the Linux, so that we need it, don't need it. And this is system and constant. Again, we have domain 0, 2, and solid. Again, check my previous videos about all these settings, and I have the boundary conditions as well to be defined for the 3 domains. So what I should do next is how to add this part of aluminum block with the heating source, right? We want to apply some heating here. For example, I want to heat the water in this condition, but it except using the hot air, I actually use some electrical heating here, for example, to heat the water, right? So how to do that? So the OpenFOAM provides FV options. So FV options is a heat source. It is a source item that can be added. So the source item includes 2 sources called explicit and implicit source. So for our application of NSAMP, so which is the energy source that will be added, we use called semi-implicit source. So that can be used for steady or transient conjugate heat transfer. So there are a lot of settings, not only for the heating, but also a lot of applications if you want to check how to set up there. So I will only focus on the energy, or mean the internal energy at this stage, right? How can we do that? We will firstly go to the solid and create a top set dictionary for the solid domain. Why? Because we want to have a solid region from the aluminum and add a cell set for the heating source. That we need to do now. So I can use the VS Code if you have used it before, because VS Code allow me to. So I can go to further. So I will go to the subfolder. So CHT demo source cdcht demo source. That's the folder. And if I use code dot, of course you can use other txt files to do this. And I will just go to the system, and I will do some definition here by adding a file called did I add that or not? I call a file called top set dict dot water. Oh no, sorry, dot solid, right? So that is what I'm going to do now, because I want to create the solid region. Here I have only one action. The action is create I will copy it first to here. So it has only one action by creating a solid region called aluminum source, and this is a cell set, which means a number of cells together, and I will use the box to cell. So box to cell is actually using box that will include a region. What I want you to see is only the x, so x from 0.09 to 0.11. So my domain is here. So from 0 to 0.2, so the center is 0.1. So left and right, it will be 0.1 millimeters. So I will use that to construct the region that can be used for the heat source. So I can use ParaView if you want to check how it looks like. So ParaView, I will go to my here. So because I have CHT demo force before, I will just rename it as source just to differ with the previous one. Then I will go to the ParaView and load that source. If you want to see clearly how it looks like, I will apply it here, and this is a domain. So if I want to include the data, I use data axis here. So the axis is from here to here, right? So this is the domain I defined for from 0.09 to 0.11. So 0.09 to 0.1, a very narrow region, from here to here, and it will form our solid. Because I'm only defining the solid region, so it will give me the solid region only. So that should be the definition for my solid heating source region. So what I'm going to do next is to create this solid region by using top set dictionary. So I use top set, and I will use the dictionary currently, and the system folder, and the name is .solid, and the region is solid as well. So if I run this, and it'll give me the aluminum source now size 40, which means I have created that region. So next step is define the FV options. It's quite straightforward. So we go back here, and we'll go to the still the system here, and also in the solid region, I will create FV options, right? So FV options, I will define as here. The FV options, we need to use the type of scalar semi-implicit source. That is source I have explained here before, semi-explicit source, and it allows me to select what kind of region I will use. I will use only the cell set mode, and the region is aluminum source within the solid region, right? And the volume mode, which means how to define the heating source. It can be specific or it can be absolute. So it means it depending on the volume or not. And now I use absolute, as the source is constructed by explicit source and implicit source. So the implicit source can be based on the on some variables, and explicit can be only a constant without any functional or spatial distribution. So I will only use the explicit source. H is our CHT multi-region solver use. So I will copy this and go to my FV options and define it here. So that is the definition of this. If I check my control dict here, so everything looks good. I will also run 500 steps with density of 1 because it's a steady simple form, so it shouldn't give any big differences. The right interval is 50, which means I will have like 50 10 steps in total. So I think I'm ready to run this. So again, all the previous setting, check my previous video. Now I just run CHT multi-region simple foam. And now the solver start run and it'll give me the results later. So after running only like 13 seconds, 12.99 seconds, it gives me the results. And what I'm going to do next is to compare the results of the previous project and current project, which means with and without heating source. And this is my plot result, but I will show how to do it now from here. So this is our current folder, which means has source, right? So if I refresh it, and it will have the results now. So this is the 3 regions. Remember, the heating source is in the center, and I can show the temperature at its final stage, right? But I'm more interested about comparing with the previous, so I will also load the previous called CHT demo and the CHT demo foam. So I will move it up to let the both displayed at the same. So I will just move by using transform, and I will move about here 0.05 on the y direction. So that will give me here the results for both. So if I display the temperature as well, and also at the final stage, I can see some differences, right? Because here the temperature is defined in Celsius, so from 20 to 200, and the biggest difference is in this region, right? The water coming from here and go out from here. So when it passes the heat source here, so previously there's no big difference, but because of heat source introduced, there will be some further increase of temperature in the interface between the solid and the water, and it's very difficult to check visually differences of the temperature for the air region, for example, but you will see a little bit difference about the contours of the temperature distribution, and also we can further compare it by using a file called plot over line. So we'll plot the current one first. So plot over line. So plot over line, not plot over time. Sorry, it should be plot over line. Plot over line. Yeah, this one. And what I'm going to do is plot a line here along the region of the air, and we'll see the difference between these two projects. Firstly, we need to define the line position. I use a position of 0.06, so the height is here, and also along the center of Z, and also here, so the same y-axis. So that is the line I'm defined, right? So from here to here, then I can apply, and it will give me some plot of many results, but I only need the temperature, so I will display the temperature only. So this is a temperature distribution of the air, so during its cooling, when it's, let's say, when it's warming the water, right? But also I want to compare the previous project also by using plot over line, and the same position as well, so 0.016, and this is 0, and this is 0. So that will give me another one along the previous. So I should plot. Sorry, I will plot at the same. So I will choose this one and plot the same. And of course, I only need the temperature as well. So that's the temperature, right? So I will show the current one in this dashed line. So current temperature in dashed line, and the previous one is in solid line. You will say because of the heating source introduced, so the air, so the hot medium temperature is not as low as the previous one, right? You remember I will have a heating source positioned here, and it also elevates the air temperature from here and beyond. So the outlet is 84 for the if introducing heating source, and the previous one is 72. So it elevates the temperature outlet by 10 degrees after reaching a steady condition. So this is an example of using heating source within the solid, but also you can also introduce any heating source in the water, air, or in different regions, different heating sources. You just define the topology of that domain and bring the heating sources within that regions, and that will give you the solutions.